Maybe we can start.
Yes. Yeah, I'm here.
Okay, very good. So welcome back everyone to the afternoon session, and we are starting with Alok Laddha from Chennai, and he'll be telling us about soft modes at Scry and the BMS algebra. Please go ahead, Alok.
Okay, thanks Sylvia, and thanks to Andrea and all the organizers for giving me a chance to speak here. So I will be telling you about some work that Miguel and I did recently about the understanding of the BMS algebra at null infinity, and how it also kind of helps us understand a final classification of the space of vacua in quantum gravity. So, So yeah, this is partly based on work with Miguel that we released in June, and of course, a lot of it is based on previous works by many other people. So let me start with some brief motivation, although Miguel kind of stole all my punchlines basically. But so we know that the super translations and super rotations are, among all the towers of the asymptotic symmetries that we are discovering, these are the most well understood symmetries. And in fact, I think we understand pretty well that super translations are exact symmetries of quantum gravity asymmetries in 4 dimensions. In the sense that in any given asymptotically flat spacetimes, we know that these are spontaneously broken, and the associated Goldstone modes are nothing but the leadings of graviton modes. And of course, in recent years, we have been able to do a lot more with this. For example, we can also classify the vacuum states, which are eigenstates of the super translation charge. And conservation law of the super translation charge between Scry minus and Scry plus basically enforces a transition between different vacua. And we can quantify this transition by the Weinberg-Sauer factor. But situation with super rotation, as Miguel was also discussing, is actually far more intricate. So unlike in super translations, where there was a beautiful proof by Karthik Prabhu in 2019 that there's a conservation law in the classical theory, we don't know if there is any such proof for super rotations. And super translation charge at Scry plus or even Scry minus is unique. But as it is, has been understood for a few years now that there is a 2-parameter worth of ambiguity in deriving the super rotation charge from phase space methods. So there is no unique or a canonical definition of what a super rotation charge is. And so there are really 2 questions that I would like to focus on in this talk. One is that, is there a way to identify the Goldstone modes associated to a spontaneous breaking of super rotation symmetry? And can we also classify the space of vacua once super rotations are included? And this is actually quite intricate, because once we include super rotations, they don't close among themselves, and we can't then ignore super translation. So we have to work with the whole BMS algebra together. And the second question, which is kind of probably the more important question, is that if you choose the simplest prescription, so there is this ambiguity, but if you look at the simplest prescription for defining the super rotation charge, then in the momentum space basis at null infinity, if you look at the algebra generated by the quantized charges, then they do not close. And in fact, it has a field dependent, or what is called a 2-co-cycle extension. This result, it was shown in a very nice paper by Distler, Flauber, and Hahn in 2018, is actually consistent with doubles of graviton theorem. So then the natural question is this full extended BMS symmetry, which includes super rotations, anomalous? But there is a sort of a paradox here, that because there are these recent works in celestial holography which show that, in fact, extended BMS algebra closes up to a possible center extension, but they certainly do not find any 2-co-cycle. And the work of Shamik and collaborators, and of Stefan and Tomasz also, they both get this extended BMS algebra which has no such field-dependent extensions. In fact, the work of Steiberger and Taylor, they really use conformal doubles of theorem to derive this closed algebra. So it seems it seems like there is some paradox between the looking at conformal doubles of theorems versus momentum space doubles of theorems. And in one case we get a closed algebra, and in the other case we do not. So we will in this talk at least try to partially answer these questions from the perspective of null infinity and momentum space of theorems. But there is a beautiful work recently which came out, I think last week, by Laura Donne and Rusiconi, where they answer precisely all these questions from the celestial perspective also. So I think there is a kind of coherence between these different approaches. And so let me make some disclaimer that we are going to work with only pure gravity. if you want to include massive particles in this analysis, it actually turns out to be quite non-trivial and requires a much more refined understanding of asymptotic Fock spaces for massive particles in super rotated background. So this is some work in progress by Miguel and his collaborators. And in this talk, we will focus on only holomorphic or anti-holomorphic super rotations, which are the one that were discovered by Barnich and Troissard, and not the the smooth diffeomorphisms. So let me start with some brief review, which Miguel already has covered. So I go a bit fast here. So we start with space of all asymptotically flat geometries, and we know that by now that this space itself can be parameterized by modes of gravitational field at null infinity at chi plus chi minus. In particular, if we just focus at future null infinity, then this data includes the what we call the shear field, which has these two components, and the metric on the sphere. And the sphere metric, if you use something like uniformization theorem, we know that all the non-trivial information in the sphere metric is in the conformal factor. So we can parameterize this data at null infinity in terms of the shear and in this the psi field, which is the conformal factor for the sphere metric. But many times it turns out more convenient that instead of working with the psi, we work with this kind of like the action for psi, which is called the Garros tensor in relativity literature, which I just denote by T. So in some sense, the complete information about the radiative data is in the shear field and in this Garros tensor. And just to make contact with Miguel's notation, he called C hat as the renormalized field, but for us in this talk, it is the C which is the renormalized field. So I will always keep the T, the Garros tensor separate. And so this is the basic phase space that we are familiar with. So we have a shear field, which if you look at the, we can always split it into a constant mode, which I just denote as C0, and in some sense what we would call the radiative part of the shear, which I denote by small sigma. And from early days of general relativity, people realized that the sigma has a particular fall off that it could go as, itself go as some constant mode, but these constants take different values at u equal to plus or minus infinity and some fall off conditions, which here I denote as, I take them to be faster than 1 by u fall off that we are discussing in Miguel's talk. And NZZ, which is the u derivative of sigma, which really contains the radiation information, is called the news. Now, this C0ZZ, I mean, it actually has two components, Z and Z bar, but for this class of spaces, which are called Kristeva-Kleinemann, and as Strominger explained in his first paper, 2013, that we can actually parameterize this constant shear mode in terms of a single function C. And similarly, for this class of spaces, it turns out that if you look at the difference of this sigma plus and sigma minus, then it can be parameterized in terms of a constant function, which I call here the script n. And because this script n is really, because sigma plus minus sigma minus is just the zero frequency component of the news, so we just call it the soft news mode. Now it turns out that for generic gravitational scattering, actually this is not the right fall off to consider. The fall off in u actually goes as 1 by u, and this is some work which has recently been done by Ashok and Vishwajit, and I think these results are also probably there in these papers of Damour and Blanchet. But the extended BMS algebra is well defined only with slightly stronger fall-offs. So that's what we are going to take right now. And as Miguel explained, this subtlety is integrally tied to the one loop exact universal log omega soft theorem, which was derived by Vishwajit, Sahu, and Ashok Sen. So, okay, so now coming back to the phase space with the stronger fall-offs, like there are these classical results that we know that the shear field sigma is conjugate to its u derivative, which is the news. However, in this classical phase space that was discovered by Asteker and Stubel, they did not include these corner modes, the constant shear, the soft news, or the Garros tensor. And as far as the corner modes were concerned, they were first incorporated in this phase space analysis by Hay, Lysov, Prahar, and Strominger, who showed that one could work quite a rigorous phase space analysis by including the C and the script and just wanted to give a warning that the T is just the Garros tensor, not the finite any stress tensor for theory. So now the analysis that HLMS did was very instructive, and that's what we are going to use later. So I'm going to just briefly review their analysis quickly. So the idea that we want to include these corner modes in the phase space, and the way to do it is to first look at the action of super translations on the full phase space data. So we know that from space-time perspective that the action on the finite energy shear is just by as the first equation, but the constant shear mode C simply shifts by the super translation, and the Garros tensor does not change. And this just comes from the space-time action of the super translation. But we could also do phase space analysis, and it turns out that the super translation charge at, say, Scri plus has the form which is written here. So if you look at the first term, you immediately notice that it kind of tells you, it's very instructive to think that so this D is just the sphere derivative, and D to the 4 I just schematically write as like the fourth sphere derivative. But so we clearly see that this D4N is sort of conjugate to C. I mean, that's what we would expect. And that's the insight that HLM has used to incorporate these modes in the phase space. So the idea is that we can start with, say, let's say like an auxiliary bigger phase space, which has this finite energy shear and a pair of soft modes, C and N. And for this auxiliary phase space, they are roughly canonically conjugate to each other, but now we have to impose constraints on them because we know that, for example, script N is defined in terms of the shear. And these constraints are simply that the shear itself has no average because we extracted out the constant shear mode, and the difference of sigma plus and sigma minus is precisely this of mu. And as HLMS showed in the paper, that these are really second-class constraints, so we have to do a little bit of the Dirac's constraint analysis. And this leads us to a more refined definition of the phase space, which turns out to be crucial for analyzing the super translation symmetries for the asymmetric. So just to give you a summary of the result, and so this phase space is more refined than the one that Ashtaka-Stubel had. So we have the usual shear and its conjugate mode bracket, or in fact, it turns out that we can also define here the bracket between shear and itself. And the constant shear and the soft news are conjugate to each other, as we would have intuitively expected. And both the soft corner modes do not have any bracket with the finite energy news. So there is really a decoupling of the soft sector from the hard sector here. And now with this phase space, we can actually quantize the super translation charge, because there's a question?
Yeah, there's been some interesting papers in the last year or two about the dual super translation modes. Yes. Could you comment on that and whether there should be an even bigger enhancement of the phase space, or how do you think about that? In this?
I think so. I mean, I think that the analysis, I mean, the way I understand your analysis and also the way we incorporated.
No, this wasn't my analysis. I didn't write any of these dual super translation.
No, this phase space that I'm just describing here. There we use the CK conditions explicitly. So I agree. I haven't looked at it, but I would expect that more modes will have to be added for the dual charges. Yeah, so now we can quantize the super translation charge on this more refined phase space. And it turns out that, as was shown by HLMS, that the Ward identity of the super translation charges precisely give you Weinberg's soft graviton theorem. And but there is more that we can understand if we use this kind of formulation of the super translation charge, in the sense that because the soft news, we can parameterize the state of all vacua in terms of the eigenstate of the soft news operators, because they mutually commute. So we can just, we can say that all the vacua of the theory are parameterized in terms of this, what I call capital N. And then the Ward identity simply turns out to be this boxed equation, which is really telling you that there's a transition between the vacua, and the difference of the the vacuum labels is quantitatively given by the Weinberg's soft factor. So that was the status with super translation. And of course, we want to understand how super rotation symmetries act on these space of vacua, for example. Now, we know from space-time perspective, so I'm just going to look at, say, holomorphic vector field just for simplicity. And we know from space-time perspective what the action of super rotations are on all the fields in our at Scri. So we know how it acts on the finite energy shear, on this Garros tensor, and also on the constant shear mode. And now we can use this standard, covariant phase space or Wald Supers type analysis to derive super rotation charges at Scri plus or Scri minus. And so this is the expression that we find. So there is a it has a compact looking expression, which is in terms of the finite energy news and the shear sigma and the Garros tensor T. And I've indicated some dot here to basically say that this this definition is actually not unique, unlike the super translation charge. So this is ambiguous up to addition of corner terms, which you can add at the boundary of Scri plus minus. But okay, we could always ask, and which is what was asked for a few years, that what if we look at the simplest possible definition, which is what I call the bulk term, which is just the first term that is written here in the last equation. And what are the consequences of using that as the symmetry generator for the superrotation? And it was shown by Hale, Isov, Pasterski, and Strominger in 2014 that if we use the simplest prescription for the superrotation charge, then it indeed gives us the tree-level subleading subgraviton theorem. So, but of course, it has been recognized for many years now that the complete understanding of superrotation symmetries in gravitational scattering is lacking, and for the following reasons. So I'll just list some of the subtleties with superrotation. One is that we know from spacetime perspective that superrotation shifts the gauge tensor, but it's not clear how to derive this from. Okay, there's a question. There's a question.
Andy, did you have a question, or is that a leftover hand? Okay. Yeah, I think you can go on.
So although we know that the superrotation shifts the gauge tensor, it's not clear how to derive this result using phase space, simply because even in the refined phase space of HLMS, the gauge tensor wasn't included. So we could say that we don't really have a faithful representation of superrotation on the asymptotic phase space. And as we saw that, when we quantize super translation charge on the radiative phase space, we got eigenstates of the super translation charge, which are parameterized by the soft news, but we don't know how the superrotation charges act on them. But these are okay, we can say these are some technicalities, but it turns out that there is a much more serious problem that we do not even have a closed algebra. And this was, I think, very beautifully explained in this paper by Flauger, Distler, and Horn, who really used just the consecutive doubles of theorems at tree level to show that if you look at the algebra generated by the super translation charge and this bulk, the simplest possible prescription for the superrotation charge, then it does not close, and it has this what we call two-core cycle anomaly. So I just schematically indicate their main result, which is that if you take the an amplitude with two soft gravitons, where one of the graviton, which I call with momentum k1, you take the leading soft limit, and for the graviton with momentum k2, you take the subleading soft limit, and you commute these two limits. Then it turns out that this amplitude factorizes into a soft factor, it's like a double soft graviton factor, and the endpoint amplitude. And these authors showed that this statement is equivalent to having an anomaly in the algebra of the super translation and the simplest possible prescription for the superrotation charge. And this anomaly is not central, and as we can see, it's actually linear in the soft news. It depends on the script n that we had defined earlier. So this seems like a little bit puzzling. Now, if you look at the classical analysis of extended BMS algebra at Scri plus or Scri minus, this two-core cycle was already derived by Glenn Barnidge, I think in 2017, definitely before Flauger, Distler, and Hall. But what happens in the situation for when we think of BMS algebra as symmetry of gravitational scattering, this becomes much more serious issue, because it looks like we have two symmetry generators, which are symmetry of the Asymmetries, but their commutator is not the symmetry of the Asymmetries, which looks very, very puzzling. So it looks like from Jacobi identity, this should not be happening. So we really have, the superrotation charge is kind of infected with three problems. One was this which is the most serious problem, existence of this two-core cycle, which seems in contradiction with basic Jacobi relations. Then the fact that we don't know how it acts on the gauge tensor, and we don't know how it acts on the space of vacua that HLMS had obtained from that quantization. Now it turns out that, okay, so the issue turns out to be obviously that which prescription should be used for the superrotation charge. And for a completely different reason, in 2017, Pasterski, Strominger, and Sasha Zibodov had proposed one prescription for what corner term we should add in the superrotation charge. And the motivation was that as they showed, that the corresponding conservation law, after they added these terms, turned out to give a prediction for what is now called the spin memory effect. And this prescription that was proposed by them, as well as the entire class of ambiguities, were investigated in more detail by Flanagan and Nichols, and also by Compare and his collaborators. And finally, Miguel and his student Javier, they used this prescription and actually showed that classically this new superrotation charge and the supertranslation charge, in fact, form a closed algebra with no two cocycle or central extension. So what we want to do is now to sort of take this as the sort of prescription and see where it leads us in quantum theory. So that's our goal. So let me just tell you schematically what this new superrotation charge is. So the term in the blue is the new term. So there is this fourth sphere derivative which acts. So as you can see, this new term depends on the constant shear and the leadings of nu. So it's a very kind of unexpected term from the perspective of superrotation, because these are really the modes that we associated to supertranslation. And this script D derivative, just for, I mean, it's not important for the talk, but the Garrosh tensor is included in it. So the definition of this fourth derivative is not just the fourth sphere derivative, but it is modified or twisted by the presence of the Garrosh tensor. And the red term was already present in the old superrotation charge, and that is simply the term which depends on the change of the Garrosh tensor that we know that spacetime action induces. So as you can see, this red term is linear in integral of not of news, but integral u times the news. So we know naively that u times news integral should be conjugate to t. I mean, this is exactly the logic that HLMS used in the supertranslation case. And just as a small comment, this in the energy space, this integral u times news is precisely the subleadings of graviton insertion. And of course, this is why this Ward identities for superrotation give us subleadings of graviton theorems. So this is the charge that we want to now work with. So what we want to do is exactly what HLMS did, but for superrotation. So that is, we want to now ask, what is the extension of the HLMS phase space? So that, because we now have to include, of course, the Garrosh tensor on which QI acts faithfully. So, it should reproduce the full spacetime action that superrotations have. And we follow exactly the same strategy that HLMS used. So we introduce a new sort of conjugate pair, is Garrosh tensor and a conjugate mode, which right now I just call a script N1. We don't know right now what script N1 is. It's just some new mode that we have introduced, some auxiliary mode. And we start with the same conjugate pair for the constant shear and its conjugate. The only difference is that the fourth derivative has been twisted by the Garrosh tensor. So in the HLMS case, C was conjugate to D4N. Now it's conjugate to D4N where D has been twisted. So the idea is that we now consider this auxiliary phase space where the soft, quote unquote, the soft phase space is enhanced because we added a new pair, T and N1. But we know that these are not independent of the shear, so we have to impose the constraints exactly as HLMS did. And it turns out there are two new constraints. So the red constraints are what HLMS already had for supertranslations, but now there are two new constraints. The fact that the Garrosh tensor, which is, if it's generated by, if you look at only holomorphic or anti-holomorphic superrotation, then the Garrosh tensor has to be meromorphic or holomorphic. And the fact that the script N1 that we introduced has to be equal to the subleadings of news, because that's conjugate to the T, as we saw in the superrotation charge. So, and these are a bit subtle constraints, they're same class, and we have to solve them. And when we do, it leads us to the physical phase space of the theory, which has the superrotation as well as supertranslation soft mode. So let me just tell you what the phase space is now, physical phase space is. And it turns out to be a little bit more non-trivial than we would have expected. So in addition to the brackets that we had in the supertranslation case, there are now new brackets. And so the star just denotes that we have solved the constraints, just to denote the fact that now there are physical commutators, physical Poisson brackets. And this O, it's not really very important for us, but it is some sort of a holomorphic projection. So there are, because of the fact that we are working with holomorphic vector fields, these brackets depend on specific projections in holomorphic or anti-holomorphic direction. But the important point is that the script N1, which is the subleadings of news, does not commute with the finite energy news, which is the first bracket. So this is a feature that we have not seen in the supertranslation case where the soft and the hard modes decoupled. In this case, it turns out that they don't quite decouple, and there is one non-trivial bracket that we see between the subleadings of news insertion and the finite energy news. But the other things are maybe as expected, in the sense that the subleadings of news is intuitively conjugate to the Garrosh tensor, and it commutes with the soft news. So that's a good thing, which is the last Poisson bracket. So that's in a nutshell, that's the new physical phase space that we have. And now with this, we can go on quantizing the new superrotation charge Pasterski, Strominger, and Zibodov had proposed for the spin memory effect. So let me just again, some consequence of the physical phase space I summarize here. So essentially, we know from HLMS analysis that the soft news is conjugate to the constant shear. And now we see that the subleading soft news is conjugate to the Gorosh tensor, which is intuitively expected. But the hard and the soft factors do not quite decouple anymore, as script N1 doesn't commute with the finite region news tensor. And now we can quantize this phase space and the super rotation charge. And there is a subtlety because the script N1 has a non-trivial action on the hard state. So we have to really take care of that.
Sorry, you have about 5 minutes left, Alok.
Yeah, I think soon, before that. So I should add one caveat that all our results from now on that I'm going to list were really derived for holomorphic superrotations, which have at most one pole. I mean, in principle, of course, it should be possible to do it for general meromorphic vector fields, but the computations became much harder, so we haven't really done it. So but we expect it to go through, but it hasn't been done yet. But now we can ask, okay, what are the, now that we have this enhanced phase space or enhanced space of operators, what is the space of vacua? And it turns out that the maximal set of commuting operators are the soft news and the Gorosh tensor. They just commute with each other, even in the physical phase space. So we already know that we had, parameterized the super translation vacua with the eigenstates of the soft news. So now we can parameterize, but we have now further parameterization in terms of the eigenstates of the Gorosh tensor. And now in this class of states, which have the super rotation and the super translation data, we can evaluate the Ward identity of the new super rotation charge. So first, of course, we have to check that the leading Ward identity is not changed. Otherwise, everything will be kind of useless. And it turns out that it gives you a nice, very analogous to what HLMS obtained for super translation. That if you look at a single Ward identity, it gives you the relation which is written in the first box, which tells you that there is a transition from, if you start with say like trivial Gorosh tensor, there's a transition to new Gorosh tensor, and the difference is quantified in some sense by the subleading Kachazo-Strominger subleading soft factor. So of course, the Kachazo-Strominger subleading soft factor is an operator. It's not a C function like the Weinberg soft factor. So this identity is not quite as simple as the one that we have in the leading case, but it's very analogous to that. And then it turns out that, well, I mean, with this quantization, we can explicitly check, and that computation turns out to be quite straightforward, that the algebra of the quantized charges actually come close, and we get a super translation back. So let me now conclude with some outlook, that the super rotation symmetry leads to, first of all, a finer classification of the vacua, which are parameterized by the Gorosh tensor. And in fact, this result that we have actually complements a very nice analysis by Nguyen and Salzer a few years back, I think, where they had already derived the effective action for super rotation mode, which was also in terms of the Gorosh tensor. But the turns out that our analysis really relied on solving these constraints to get the physical phase space. And this turns out to be much more involved if we look at the smooth diffeomorphisms as opposed to the holomorphic super rotations. So this is something that we have not been able to do yet, but because of work of Donne, Pasterski, and Andrea, we know that there is a nice relationship between at least in the conformal primary basis, between the soft modes conjugate to the super rotation and the smooth diffeomorphism. So maybe it will help us in sort of analyzing physical phase space even for smooth or generalized BMS symmetries. And finally, one question which Miguel also mentioned is that it would be nice to understand if there is a classical conservation law proof for the new super rotation charge, which we know leads to spin memory. Nice expression for spin memory. I guess Miguel already explained this a lot, that in QED, the fact that the asymptotic states are dressed, if we go beyond leading order in the coupling, leads to a modification of the asymptotic charges, and we at least seem to get Ward identity which are consistent with the universal one loop exact soft theorem that Vishwajit and Ashoka derived. So what about super rotation? Is there a way that we could generalize this to go beyond leading order? And yeah, I will conclude here. Thank you for listening.
Thanks very much, Alok, and for keeping to time very nicely. So we have, I think, about 10 minutes for questions and comments. Okay, so while people are, I don't see any raised hands yet. Can I ask you a very basic question?
Yes.
So you were in the beginning of the talk, you were saying how the commutators failed between the super translation and super rotations.
Yes.
So if I think of how these guys came from the bulk, then when I commute them, the thing that comes out should still be something that's, you know, taking some diffeomorphism, but then giving it a non-trivial fall off. But the problem you're saying, it's still that that guy is not a symmetry of the S matrix, or?
Yeah, so at the level of vector fields, if you look at the commutator to leading order in 1 by R, there is no problem. And even if you go beyond leading order, for the vector field commutator, of course, Barnich and Croisset have shown that there is this modified Lie bracket that you have to use. And that closes, into a super translation. If you look at the vector commutator of the vector field for the super rotation and super translation. But for the charges, it turns out that if you use the old prescription for the super rotation charge, then the commutator had this new term, and it was just what double soft theorem would tell you.
So it's the charges that gave you the issue, rather. I see. Good. So I think we have a question from Prahar.
Hi, Alok. So I wanted to ask you about in the inclusion of the anti-holomorphic vector field. So if I understood correctly, you only considered the phase space extension if I do holomorphic superrotations, correct?
No, it's just for the talk I didn't include. I mean, the anti-holomorphic goes exactly the same way. I mean, it doesn't, we can include them. The only thing is that for the final part of the analysis, we could only do these things if either of them have only one pole. You know, if you have more, then we have not been able to complete the analysis. I mean, we expect it to go through, it's just technically more complex.
I see. Okay.
Sorry, if I could follow up on Prahar's question. So in the celestial formalism where you represent the currents by, represent the symmetries by currents, there's it's not understood. It's a little bit too much to say that there's a sharp paradox because it hasn't been addressed that much, but it's not understood what to do when you have both holomorphic and anti-holomorphic, and in particular whether the Jacobi identity is a bad. And I mean, in my recent work, I just avoided all this by never considering anti-holomorphic. Yes. So do you run into this? You don't see any sign of a problem in the...
No, as far as I understand, that issue will not arise. I mean, in the sense that if you look at the either holomorphic or anti-holomorphic vector fields, we don't seem to get any additional problem. The two-core cycle that Flauger et al. Had seen was, of course, true even for just for holomorphic vector fields. It was not something that they only encountered if you had, you know, mixed above either holomorphic or anti-holomorphic vector fields.
When you say you have only holomorphic ones, that means you're putting the pole, only one pole, you're putting the pole at infinity? Is that?
Yeah, right now, I mean, for the analysis we do for the commutator in the quantum theory, we put only one pole and we just put it at infinity because the brackets are more complicated if you have more poles. I mean, that's
right. So that might be exactly where we're seeing the problem is.
I see. Okay.
Is at the pole. So.
Okay. We have one pole. We have just one pole. Yeah. Right now.
So you wouldn't be able to derive the double soft theorem, like with one positive helicity and one negative helicity, because you need to have two poles, both in the positive helicity mode and the negative helicity mode to write.
Yeah. So speaking right now, yes, we have not. We are still trying that. Yeah, exactly. But just that the only thing I wanted to say that the two-core cycle that Flauger saw had a different origin. You know, it didn't come from the multiple poles. It just came from the fact that the old super rotation charge was not compatible with double soft theorem. I mean, that was the...
I think there's a question from Tristan.
Yeah. So actually, I think maybe you've answered my question, but I'm not sure. If I wanted to repeat the analysis of Flauger, Dissler, and Horn, Yes. So it's the relationship between the charge and the soft limit that's changed. Is that right?
The relationship between the yeah, I think I understood your question. So now, if you want to repeat the Flower-Dister analysis, the equation that I've shown here in this box here, it will tell us that the commutator of the consecutive doubles of theorem that is equivalent to not the commutator of the two charges, but that plus an extra term.
And that term would cancel this central extension.
No, so in that case, so I'm saying that the if you look at this box equation here, that is here, and if you replace qy with qy new, then we know that this qy new closes. So that means that the top line, which is the commutator of two doubles of theorem, that full equality is not equal to the commutator, it's equal to commutator plus an extra term, which is the k.
I see. Okay, thanks.
So that is just a reformulation of their statement. Yeah.
Yeah, thanks.
But by the way, that commutator, that extra term, if you make everything holomorphic, you can integrate by parts, and if the pole's at infinity, you won't see anything. So they might be related.
You mean this k term?
Yeah.
I see. I think the k term, even for holomorphic, it does not vanish. I don't know. Maybe if Miguel is there, maybe he can answer. I think it's still there. The term is still present.
Yeah. Why would it vanish?
Well, if f is holomorphic and y is holomorphic, we just integrate.
Oh, sorry. F we do not take to be holomorphic. Sorry. F is not holomorphic for us. Only y is either. I mean, only y has one. F is not holomorphic.
Yeah, and script n also is not.
Yeah, it's not holomorphic.
Right, but in the celestial version, one takes f to be holomorphic or
okay. Yeah, okay. Sorry. Yes, here we do not take f. F is just root for us. Yeah.
Okay. Do we have any other questions for Alok? If not, maybe we can move on to the next speaker.
Thank you.
Thanks again, Alok. Yeah, let's thank him again. Sorry, we can't really clap, but yeah, thanks for the nice talk. And I think we have Mark Henneaux next.
Yeah.
So if you try to
share my screen, I guess.
Share, yeah.
Yeah, share the screen. Let's see. Can you see my screen?
Yes, maybe if you can, yeah, make it full screen as well.
Is it full screen now?
Not. Oh yes, now it is. Now it is.
Okay. So I can start.
Yeah, if you're ready to start, then we'll continue with Mark Henneaux from University of Brussels with analysis of asymptotic symmetries at spatial infinity. So please.
Thank you very much for the invitation to present recent work. So actually a more accurate title would be, let's say, analysis of asymptotic symmetries at spatial infinity, the case of supergravity, since I will concentrate in my talk, I will focus exclusively in my talk on supergravity. But that illustrates general ideas. So I would like to describe, to make the asymptotic analysis of supergravity at spatial infinity in the asymptotically flat context. And the results I'm going to present in this talk are based on joint work with these persons, which we just put on the archive. And our central result is that with the definition of the theory, so if you add to the Lagrangian boundary conditions at spatial infinity, so you make precise the decay rates at spatial infinity, this is what I mean by boundary conditions, you end up with an asymptotic symmetry superalgebra, which is an extension of the BMS4 algebra with an infinite number of fermionic generators. And furthermore, these generators are the square roots of all the super translations. So that generalizes the known fact of rigid supersymmetry that if you take the graded commutator, so the anti-commutator of two supercharges, you get translations. But here we get the same, but for the super translations. And I will not report here the full analysis because it has some technical aspects, but I will focus on a point that intrigued, which we did not understand immediately and kept us intrigued, which is that in the way we define the asymptotic supersymmetries, we get nonlinear terms in the algebra of the charges. And I would like to explain why these nonlinear terms are in fact, so which are quadratic to be more precise, these quadratic terms are in fact necessary. So that will be the main point of my talk. And so the approach which we have followed is a discussion of asymptotic symmetries in the Hamiltonian formalism, so where the fields are given on space-like hypersurfaces, Cauchy's hypersurfaces, and we give decay rates at spatial infinity, and we want, with these decay rates, to see whether we can define charges and generate canonical generators for all the symmetry transformations, and what is the algebra in the Poisson bracket of these generators. And we did that with Cédric Troussard in the n equal to 0 case, so pure gravity, and we wanted to extend that to supergravity. But the key thing that on which we insist is that we have a finite action, so a finite symplectic structure in particular, since we read it from the action. We have, oops, it doesn't seem to, Then we define symmetries as symmetries which preserve the asymptotic fall-off. So gauge transformations in our case that preserve the asymptotic fall-off. So they move a point of phase space into a point of phase space, and phase space is defined by the fall-off conditions. And it leaves the action invariant also, and then you have a well-defined moment map, that is, you have a well-defined canonical generator. And then you can apply to these canonical generator standard theorems of Hamiltonian mechanics and use a Jacobi identity for the Poisson bracket, etc. Now, there exists, as always, I mean, the Lagrangian does not completely define a theory. You need boundary conditions, and there are different approaches, at least two, but there are more, I'm sure, to the study of the asymptotic structure of supergravity. And they lead to different fermionic extensions of the BMS4 algebra. Now, the first approach, which is technically the simplest, takes as asymptotic conditions on the gravitino field that it should decay as 1 over r squared. So I'm considering simple supergravity in 4 dimensions, for space-time dimensions. And because you take and now this is motivated by the fact that the supercharge is a surface integral of the gravitino field undifferentiated. So if you want to have a non-vanishing, non-singular and supercharge, it's natural to take the gravitino field to be 1 over r squared, since the surface element goes as r squared. But if you take that, you quickly see that the supersymmetry parameter of the gauge transformations, since psi I, the gravitino field, transforms with the gradient of the supersymmetry parameters, the gradient should go as 1 over r squared. So the supersymmetry parameter itself should go to a constant plus something of order 1 over r. And it is really the leading behavior, the O1 behavior at infinity that determines the non-trivial supersymmetry transformations. And since that has to be a constant, that means that you have a finite number of fermionic symmetry transformations. And that is perfectly consistent, but you get a super BMS4 algebra, an algebra with a finite number of fermionic generators, which close on ordinary translations, as I recalled a few slides ago. And this is actually an algebra that was considered some time ago in the context of null infinity studies by Awada, Gibbons, and Shaw. And they found a way to realize it at null infinity, and that can be done also at spatial infinity. But there is another possibility. And that other possibility, well, you have to take more flexible boundary conditions on the gravitino field. So instead of requesting that it goes as 1 over r squared, you allow for a term that goes as 1 over r. But if you just take anything that goes as 1 over r, there are many things that diverge. So, and it's not obvious how to control them. So we took the 1 over r term in psi I to be of the specific form of a gradient. So the leading piece in the supersymmetry transformation of psi I. And then, not surprisingly, if that can indeed be consistently implemented in the Hamiltonian formalism, and you can check that the symplectic form is finite, you can associate well-defined canonical generators, etc., that will clearly lead to an infinite dimensional fermionic extension, because chi itself is an arbitrary function on the two-sphere. Now, it turns out that we have to take it to be even to eliminate some divergences, but that as a group theoretical interpretation in terms of representations of the Lorentz algebra, so it's something which is natural to do. And we found that indeed we have an infinite dimensional fermionic extension, and that the fermionic generators that will be parametrized by functions on the two-sphere are square roots of the BMS4 supertranslations, in the sense that if you take the graded commutator of two supersymmetry transformations, one parameterized by epsilon1, which is a function of the sphere, and the other by epsilon2, a function of the sphere, so that's the leading order of chi, you get a BMS4 supertranslation, which is parameterized by, well, I will explain the parametrization here, but by T and W, which are functions then, since epsilon1 and epsilon2 are functions on the two-sphere, T and W will be functions on the two-sphere, and this is the Hamiltonian parametrization of BMS4. So that was considered by Cedric some time ago, and we made some formulas more explicit later. But the idea is that, so this is the Hamiltonian description on space-like hypersurface. So a diffeomorphism will have a normal component, which turns out to be T, and a tangential component, which is constructed out of W in this way, with T even and W odd. And they are related to the alpha function, which appears in the description of BMS4 supertranslations at null infinity. Not just that the even part of alpha is T and the odd part of alpha is W. It's a bit more complicated, but essentially this is the idea. And yeah, I should say here that something else that I should, in the formula giving W, there is gamma I, these are the standard gamma matrices. There is also Ni, which is the normal to the unit sphere, to the sphere, which depends only on the angle. So W depends only on the angles. So it's indeed a function of theta times I. Okay, so this is what we found. We found an infinite number of non-trivial supersymmetries, and when we see how they close on supertranslations, and on all of them. This is what I just said. The graded Poisson bracket of the asymptotic supersymmetries, one with parameter is just a BMS4 supertranslation, which you can write this way. But I mean, symbolically, there is some gamma, okay. Yes, you can write it that way. Okay. And this, we were in a sense happy with this, because this is the asymptotic form of the well-known fact that the anticommutator of two local supersymmetry transformations epsilon 1, epsilon 2, is a diffeomorphism parameterized by this psi mu. And if you take the asymptotic limit of that formula with the boundary conditions that we gave, you get exactly what I wrote. Okay, but then, so that was nice. But then when we computed the other Poisson brackets, we got something that at first we did not understand. And I would like to address this issue now, because there is a quadratic term which arises in the algebra. And to understand the need for the quadratic term, I have to make a digression in which I will recall some basic features of the theory of infinite dimensional representation of the Lorentz group. Now, maybe it's not completely necessary at this workshop to do that, since the two sphere at infinity is just like the celestial two sphere. A two sphere is a two sphere. And so if you know how the Lorentz group act on a two sphere, this is what I'm going to really use. But nevertheless, since some of the notations and conventions and features I will mention are relevant to the analysis, I will recall the representations of the Lorentz algebra. Okay, the reason in our present case that I need that is that the parameters T, W parameterizing super translations, which are functions on the two sphere, and the fermionic parameters, which are the square root of the super translations, are functions on the two sphere. So we need really infinite dimensional representations of the Lorentz algebra, which, okay, now the representations of the Lorentz algebra, all of them, not just the finite dimensional one, have been studied by Arishandra and Neymark and Gelfand and Neymark. And I will actually use the convention, the terminology of Gelfand and Neymark. So here is the Lorentz algebra. The A's are the rotations generators, so of the compact subalgebra SO3. B are the boosts. They transform as vectors under, and this is the second line, as vectors under rotations, and the commutator of two boosts give me a rotation. So this is a familiar Lorentz algebra. And to describe the representations, it's useful, well, we know that very well for SO3, to introduce H3, H plus, H minus. H3 is Hermitian. H plus and H minus would be the raising and lowering spin along the third direction operators. And you do similarly for the boost. That's useful. So there would be a B3, IB3, sorry, which is F3, and F plus and F minus. Well, I think this is quite familiar, I think. And then how do you describe the representations? Well, the general results, as I said, have been derived some time ago. And since SO3 is a compact subalgebra, you know that any representation of the Lorentz algebra will be also a representation of SO3. And so it will decompose as a direct sum of representations of SO3, of irreducible representation of SO3, RL, characterized by the SO3 spin, so L, which actually Gelfand and Neymark call the weight of the representation. So usually we think of weight as weight of states, but here okay, so I will use the terminology SO3 spin of the representation, which is, as we know well, a non-negative integer or half integer. And in the case of representation of the Lorentz algebra, if you do make a generic irreducible representation of the Lorentz algebra, will give you an infinite sum here. You would have many SO3 spins occurring in the decomposition, even if the representation of the Lorentz algebra is irreducible. But one thing that has been shown in this analysis is that if a representation RL occurs, of SO3 occurs, it can occur only once. So it will be non-degenerate. So either it does not occur or it occurs, but if it occurs, it's once. And furthermore, if you call, then you can look at the representation with lowest SO3 spin. There are integers or half integers which are non-negative. So there is one such L0. And you can show that all the SO3 spins that will be present in the irreducible representation differ from that value L0 by integers. So you will have L0, L0 plus 1, L0 plus 2, etc. And if the representation R is finite dimensional, it will stop at some maximum value, L0 plus n, where n is an integer. And if it's infinite dimensional, it will not stop. And both cases have been considered by Gelfand and Neymark and Arish-Chandra. And the presentation of, now they explicitly constructed the matrix elements of all the operators. Now, for the rotation generators, it's easy. I mean, these are the familiar angular momentum formulas. So psi LM form a basis of the invariant subspace for SO3 RL, and it's just a standard formulas, as I said. And M, as we know, will go from minus L to plus L. Now, just notice, and this is something that they used to present the formulas which are on the next slide, that these formulas are invariant if you rescale all the vectors psi LM by some factor which only depends on L. So in the same RL, you rescale all the vectors. Of course, you will change the norm, but I'm not discussing unitarity at this moment, or scalar products at this moment. So if you just rescale by a common factor all the vectors of some invariant subspace, the formulas will still be the same. And actually, using that rescaling, they provided the matrix elements of the boost operators, well, which to a large extent, you know, will be very much constrained by the fact that they are vector operators. So the Wigner-Eckart theorem tells us that they can only connect SO3 spins which are related to, they can change the SOC spin only by 1, -1, or don't change it at all. So there will be only 3 non-trivial sets of matrix elements, and E they are. Now, this is a formula that actually is not, these are formulas which are actually not too difficult to derive, but the important thing is that there are some parameters which appear here. So, and this is what I want to discuss. So don't try to recall the formula, but you see that there are CLs and there are AL. So to completely specify these matrix elements, or to how the F3, F plus, F minus act on the basis vectors, I have to tell you what are CL plus 1, so CL for all values of L, and AL for all values of L. And once you know that, you know completely the representation. So what are CL and AL? Well, they showed that they depend on some other parameter L1. So they depend on L0, the minimum value of the SO3 spin, but then there is another parameter which appears, which is free, so which appears in the, which characterizes the irreducible representation, which is L1. And L1 can be an arbitrary complex number. And so a reducible representation of the Lorentz group is completely determined by a pair of number L0 and L1, where L1 has a very clear meaning, and L0 has a clear meaning, and L1 is an arbitrary complex number. Now you can see that in these formulas, L0 and L1 are enter completely symmetrically. In AL, that's obvious, in CL also. But the symmetry is not perfect because L0 has to be an integer or half integer, while L1 can be an arbitrary complex number. Now, as I said, the representation with SO3 spin L0 will contain the value L0, L0 plus 1, L0 plus 2, etc. It will stop if at some point CL vanishes, which will happen if L1 is equal to one of these values allowed for L, which are L0, L0 plus 1, L0 plus 2, etc. And so that will happen if L1 differs from L0, well, since we have only L1 squared, so it's really the absolute value of L1 differs from L0 by an integer. And then you can show that the maximum spin that will be present is L0 plus n, if L1 is L0 plus n plus 1, okay? But in the other cases, the representation will be infinite dimensional. It will start at L0, but it will never stop. You can increase forever, the SO3 spin forever. Now, they also analyzed when it was unitary, although I will not use that here. Let me just mention L1, so it will be unitary in only two cases, L1 pure imaginary, and no restriction on L0. This is what they call the main or principal series, or L0 equal to 0, and L1 real number. This is what they call the supplementary, which is called the supplementary series. And you can see that only since if L0 is to differ from if L1 is to differ from L0 by an integer, that will not, finite dimensional representations are in general not unitary except the trivial ones, the trivial one. Okay, now, why is this relevant to the asymptotic structure at infinity? Well, because super translations form representation of the Lorentz group. And in infinite dimensional one. And now the super translations can be described by one function which has both an even and odd part on the two spheres. So you can combine, as I mentioned, T and W, which appear in the Hamiltonian description, into a single function on the two sphere, as it is well known. Well, I called it alpha, now it's called tau, which transform under the Lorentz group. Well, under rotation, that's pretty clear. Under, well, you have a conformal action under boost, and that can be written explicitly in this way in terms of the boost vector. So that will, which bi xi, you can write it as b r, okay, and this function b on the two sphere enters, well, defines the conformal killing vectors and will enter the transformation of the function tau under the Lorentz group. And there is an extra term b tau, which is a multiplier type term. So it's really a multiplier representation of the general type, which I have written down with k is equal to 1. Well, this I think is rather familiar. If we want to decompose a representation in terms of irreducible representation, then we know that there is it's not irreducible, it is reducible. There is a four-dimensional invariant subspace given by the spherical harmonics with n equal to 0 and n equal 1, which are just the ordinary translation. So this is very familiar in terms of Neymark and Gelfand parametrization. That representation as L0 equal to 0 and L1 equal to 2, because it stops at spin SO3 spin 1, and which means that L1, which is a higher spin plus 1, is 2. And then the quotient representation. So if you quotient the full BMS4 super translation representation by this invariant subrepresentation, you find that the quotient representation is irreducible, infinite dimensional. It starts at SO3 spin 2. And then it goes on forever. And the reason why it goes on forever, you can compute the other parameter is L1 is equal to 0. And L1 does not differ, is not L0 plus a non-negative integer. So it's infinite, it never stops. It's infinite dimensional, and this we know very well. So these are just the higher order spherical harmonics. Now, although the quotient representation is irreducible, the total representation, the full BMS4 super translation representation, is not decomposable. It's not fully reducible. We don't get a direct sum, because when we compute the bracket of two higher harmonic super translation, we can produce lower order ones. Okay, so it's not. This is not an invariant subspace. Now, the second representation in the terminology of well, introduced, I think, by Gelfand and Neymark, is called the tail of the finite dimensional representation with L0 and equal to 0 and L1 equal to 2. So you see that you just exchange, so some kind of duality between the two. and the finite dimensional representation would be the head. Now, we are not going to take the quotient by the infinite dimensional tail. We keep everything, as we know, describing the BMS4 super translations. Okay. As I said, I mean, compared with the Hamiltonian parametrization, where we had this T and W, T even, W odd, it's just a change of basis in the representation, but it's completely equivalent. Okay, now what about the spinor representation? So this would be given by spinor on functions on the two sphere, which actually are even. We will take them to be even. Well, this is requested by the Hamiltonian formulation when you analyze charges, symplectic structure, etc. But from the group theoretical viewpoint, it also makes the representation irreducible, because we can see, that will come in the next formula, that if you look at the transformation law under the Lorentz boost, so xi perp would be the component of the diffeomorphism corresponding to the Lorentz boost. Okay, and if you compute that for Lorentz boost, you can see that the parity of, you can expand that.
So you have about 5 minutes left.
5?
Around 5, yes. But there's 10 minutes for discussion after, so maybe
I see.
Go a little bit into, however you want to do it.
So, well, thank you for telling me, because I thought I had more time, so I will a little bit speed up. So, guys, the interesting thing is that the spinor representation is infinite dimensional. It starts with, it has spin 1/2. There is a head, which is just a spin 1/2 representation of the Lorentz group, characterized by these values of L0 and L1. And there is a tail, which is characterized by the dual value, and which is infinite dimensional. And so you have all spins starting from 1/2, 3/2, and then it goes on all the way up to infinity. Okay, but it's again not an indecomposable representation. It's not a direct sum. The infinite dimensional space is not invariant. Okay, so let me say why we need quadratic terms in the algebra. So now I come back to the dynamical realization of these symmetries in terms of the supergravity fields. As I said, the fermionic symmetry is closed on super translations, and we have some simple formula. But the problem with this simple formula is that it gives you objects that do not transform as BMS super translations. So they do not belong to the representation of the Lorentz group that I indicated. And this is a problem because that, the finite dimensional heads, which are just the standard rigid supersymmetry transformation, of course, perfectly match. They reproduce the well-known relations characteristic of rigid supersymmetry, with the translation being here parametrized by the spherical harmonics of order 1. But if you look at the tails, so the infinite dimensional part, which is in a sense the most equally interesting, I should say, then we have a clash with the transformation properties. And this will conflict with the Jacobi identity, but I told you that if you do the Hamiltonian analysis correctly, Jacobi identity should hold on the Poisson bracket. I mean, that's the symplectic form is closed and the brackets then obey the Jacobi identity. And the reason why it conflicts is that we know very well that the Jacobi identity will constrain, this being the generators of F being the generators of the boost, well, the Poisson bracket of the supercharges should be an object that transform in a way compatible with the way each individual element transform, which is the content of the Jacobi identity when you take 2 Qs and 1 F. And as I said, this is not the case. So where is the problem? Because if you compute the action of the boost on the super translation using the 2 sides of the Jacobi identity, which I have written in this way, I can rewrite the Jacobi identity this way, I have a problem. And what is failing in the argument is in fact that the bracket, the Poisson bracket, giving the transformation of the fermionic generators on the boost is modified by quadratic terms. And to be more precise, there is a second fermionic symmetry, which I call S, which is a fermionic symmetry which transforms exactly under the representation of the Lorentz algebra, which the spinorial representation of the Lorentz algebra, with a non-vanishing central charge. Actually, Q with S is 1. And this second fermionic generator appears in the bracket of the first fermionic, the standard supersymmetry or angle-dependent supersymmetry transformation with the boost. You get some quadratic relation of this type. So I want to convey the idea, so I'm not going to give the explicit formula, but you find that Q with F will give the linear transformation of Q, which is what you need to get the fermionic representation. But on top of that, there is this other fermionic symmetry which appears with so you get a quadratic expression with the generators of super translations. And if you include these terms, you can verify that the Jacobi identity holds, namely, why? Because there will be extra contribution to the anti-bracket of this with Q. Well, we had the QQ term, which was problematical, but you see that when you take the bracket of Q with SP, because there is a central charge, you will again produce terms proportional to P, and that will lead to what was missing in the transformation rule for P. And so you find that with these extra terms, which are indeed present if you do the computation, but somehow we did not understand the origin to begin with. So if you do the computation right, in a sense, you get these extra quadratic terms, and Jacobi identity indeed holds as it should. So this nonlinear term in the Poisson bracket algebra, in fact, and that's, we were misled in a sense by the linear theory, because you don't see them in the linear theory. But there is no contradiction in the linear theory either, because the gauge supersymmetries of the linear theory are abelian exactly. So you can only, you have the square roots of the ordinary translations, which are by the rigid supersymmetries of the linear theory, but the gauge supersymmetries that come from the gauge symmetries of the gravitino field are abelian in the linear theory, and so this phenomenon does not occur. So, and actually one can lift it to with some other boundary conditions to the full theory, but it's in a sense less interesting. So what I wanted to emphasize is that the heads behave correctly when you compute the square root of the heads, but we have problem with the tails. But if we include the nonlinear terms in the algebra, also we can get square root of the tails of super translations. So since I have probably now only 1 minute left, I'm not sure, let me just conclude. As always, we can always invent different asymptotic behavior for any Lagrangian, in particular at spatial infinity, that would define a consistent theory. And in the case of supergravity, there are many inequivalent ways to define the asymptotic behavior of the field. One leads to a small super BMS4 algebra, and the other leads to a big, with an infinite number of fermionic generators, super BMS4 algebra. But an interesting feature which emerges in the canonical realization is that you have these nonlinear terms in the Poisson brackets. And both contain, if you look at just the super Poincaré subalgebra, which is contained within this infinite dimensional superalgebra, they contain the familiar relation that the anticommutator of two fermionic generators is a translation. But we have also the same with tails. So we see that nonlinear terms can appear in the algebra of asymptotic symmetries, and that is important. They are, of course, constrained by the Jacobi identity. And in our case, seem to be unavoidable because of the way we define the action of super symmetries, but we did not fully explore whether one could not remove them by redefinition of the generator. So whether these nonlinearities were, let's say, intrinsic and unavoidable, like in, say, nonlinear W algebras, which also arises in some contexts as asymptotic symmetries. But there, and then we have there. So this is not the first instance where we have nonlinear terms. Here we have not studied whether they were removable by redefinitions, but we know that if we want to have a simple anticommutators for the supersymmetry transformation, then we need the quadratic terms in the bracket. And so with this, I will thank you.
Okay, thanks, Mark, for the very nice talk. And do we have any questions? Andrea?
Yeah, thanks a lot for a very nice talk, Mark. Do you have an intuitive understanding why the construction of this simplet enhancement of large supersymmetry at spatial infinity is so much more intricate than at null infinity, where it seems to be much more straightforward?
Well, as it was already pointed out many times, the comparison between null infinity and spatial infinity is tricky because you have to integrate equations. We insist of having a well-defined symplectic structure, which is invariant strictly and not just up to boundary terms in the Hamiltonian formulation. And I think that this is, and then we can apply standard Hamiltonian techniques, so there is no flux. And for that reason, I think that we have difficulties. I mean, it's more complicated. I don't know if, did you hear me? Yeah, because yeah.
Oh, I think she was frozen for a second.
I'm sorry, I seem to have been kicked out of Zoom just for the answer.
Yeah, I'm sorry that something froze, but...
Yeah, I'm sorry, I just didn't get the answer.
So should I repeat it or?
Well,
it was a very, it was not really an answer. I was just saying that we are insisting on having a symplectic structure which is strictly invariant and not invariant up to surface terms and finite. And this put very strong constraints, at least in the Hamiltonian description at spatial infinity. So this is probably the origin of the complications. But doing this, the bonus we get is that we can reliably use the Jacobi identity rather blindly, and the symmetries are canonically realized, and all the theorems of Hamiltonian mechanics apply.
I think Prahar had a question as well.
Hi, Mark. I wanted to ask you about this you said there's a new fermionic generator F that you have to introduce to get the algebra to
Yes. Mm-hmm.
So first, is that something a special feature of supergravity, or would you expect that also to be there if I was looking at supersymmetry? Say a SUSY extension of the large gauge algebra.
Well, I think actually that this is probably something that can be made rather general. You see, here we are, if you compare the theory with a finite number of supersymmetries with the other one, we are allowing a milder behavior at infinity. And I think that if you do that, you will produce extra charges. And so I guess in the bosonic case, that if you said, well, I will look at things that blow up at infinity, not as R, but R squared. And if you can have that in the formalism, you would have, I would think, both additional charges and nonlinear terms in the algebra.
Okay, so on that note,
I don't think it's specific to supergravity.
Okay, that's actually good, because on that note, I'll just make a comment. In one of our previous works with Andy and Temple and Thomas, we looked at the asymptotic symmetry associated to the soft Fortino theorem, which is in pure supersymmetry, n equal to 1's supersymmetric QED. And we found an infinite dimensional fermionic algebra, but that was not the extension of SUSY. So I was wondering whether that, and we never actually figured out what these new set of fermionic symmetries actually are. Okay. We know that it has to be there because of the soft Fortino theorem. So I was wondering if those symmetries could be associated to these extra F generators that you had to introduce to get the algebra to close.
Yeah, that would be interesting to explore indeed. Yeah, thank you.
Andrea, did you have another question?
Yes. So
well, first, maybe I can add something that it seems that if you look at gravity in higher dimensions, you get proliferation of such extra symmetries. And also nonlinear terms in the algebra. Okay, so sorry, Andrea,
Yeah, so what you found now is, I think, would be equivalent to the leading soft Gravitino theorem, right? At the boundary conditions that you imposed. There's also a subleading soft Gravitino theorem, which would have more relaxed boundary condition. In particular, some component would have order R follow at non-infinity. I'm not sure what the equivalent would be at spatial infinity, but probably just the relaxation of the boundary conditions that you put. Have you thought about that?
Well, since we have two sets of fermionic generators, there should be two different soft theorems associated with them. And I think that actually the one associated with the other generator could be the subleading soft, I mean, the next soft theorem. Because you can, well, of course, it's an expansion in powers of 1/r at spatial infinity. To relate that to expansions at null infinity is tricky, but somehow this other symmetry is related to the fact that we are exploring deeper into the structure because we have gauge transformations that behave more, that increase faster at infinity.
But this new fermionic symmetry, does that come from imposing the same boundary conditions, the ones that I showed at the beginning, or are they, because at null infinity, the subleading soft Gravitino would come from even more relaxed, and there would be, so the leading one would start at order 0 in the 1/r expansion, and then the subleading would start at 1/r.
Yes, but you see, R doesn't mean the same thing. I mean, it's a two.
I understand. That's why I'm asking whether for you they would appear at
the fact that we have two sets of charges, if you want, I mean, they will clearly be word identities for the two. And what else could they be than I mean, I think that we would just reproduce it on an analysis on Cauchy hypersurfaces and in the old ways of computing and the consequences of word identities, you would get the same. So I have that, we have not proved it, but I would think that we have two, and that's probably the same two.
Thanks.
I had a question as well. So here you're starting with n=1 with minimal supergravity, right? Have you thought about if you're doing, say, maximal supergravity or something with a lot more SUSY, would you be more constrained in what fall-offs you can have, or do you think it wouldn't help?
Well, actually, it's an interesting question, and we are indeed looking at, it's a natural question also, so we are looking at that indeed. Well, I would think that you keep the same boundary conditions on the graviton. Each gravitino will have the same boundary conditions. So in that sense, it will be the same. But then you have the vector fields, and you would have angle dependent U1 symmetries for the vector fields. And all of them would form some nice algebra, but we have not worked out the detail. But I would expect that the boundary conditions to be imposed at spatial infinity will just be the extension, direct extension of what we already know.
And do you know, this is just like a reference, but do you know if anyone has thought about like supergravity models that have some nonlinear SUSY to begin with, like a Goldstino in there or something?
I think in the old days, yes, no? I mean, maybe even the first model, I don't know. I think the answer is yes, but I could not give you an explicit reference.
Good. So maybe then if there's no more questions, we can thank Mark again. And I think now we are going into a break.